So, good morning, everybody. I would like to welcome you back to our conference, SUSEN 2020. We are just after our two parts and about to start session number 3. This session will be started with the presentation on non-destructive testing of concrete in civil engineering by our colleague Zbigniew Hlaváč. So we give him a few seconds to connect and to project. So Zbigniew, are you there?
Yeah, I'm here.
Okay. So if you can please present your screen, if you can switch to presentation.
Hi. While
Perfect. Something is happening. Thank you. And yeah, perfect. So I think it was too quick.
Okay.
So yeah, here we go. We can see it perfectly. And yes, you can start. And please, there was some small comment. If you can talk more loud, that everybody from audience can hear you. Thank you very much. And please begin.
Okay, so thank you for letting me introduce my work. I will talk not only about my work, I will talk about all the things about concrete which are done in CVR, Research Center. Presentation I prepared with my colleagues Patricia and Jan. So I will talk about all the things that are connected with irradiation and about concrete. In CVR, we can irradiate by neutrons or by photons. Neutrons are emitted by a research reactor LVR15, which is on the left-hand side picture and also on the top right-hand side picture. Photons of gamma radiation are emitted by gamma source cobalt-60, and the gamma irradiator chamber you can see on the bottom right-hand side picture. What I would like to talk about, so this presentation is especially about non-destructive testing methods. Those methods have been developed mainly in SUSEN project and also in our Research for SUSEN project. We are targeted for the mass change methods. Then we are trying to find the volume change. It is radiation-induced volumetric expansion. And also, what is my major? So we are interested in mechanical properties change. The mass change we can measure by very accurate scales. I think the accuracy is about 1/10 of microgram, which is sufficient even for very small samples. Volume change, it can be detected by various methods. We are using dimension measurement or density measurement. Density can be done by water or helium picnometry. So something about the dimensions measurement in the hot lab. So recently we have a system Vertex, which is the 3-dimensional measuring gauge. It is a system where you program what you want to measure in which positions of which sample. You have to define what is the shape of the sample and the preliminary volume and dimension. And then you can decide for optical or mechanical measurement, and you measure the sample in the way that you programmed. So on the left-hand side picture, you can see the program. You can see some small results where you see graphical visage of the surface of the sample which you measure. So you can see some differences, you can see mean values, some deviations. On the top right-hand side picture, you can see the view to the chamber, to the hot lab. So the system, which is the white machine, there is also manipulator which works with very high dose samples. The radiation of the samples, the activity can be about the millisieverts per hour on the surface, which is quite high. On the right bottom right-hand side picture, you can see the view to the camera. There are cameras inside the chamber just for you to have a better view what you do, what you measure. Let's go on. Other things and possibilities how to determine volumetric expansion. Pycnometries. We are using water or helium pycnometry. Water is very, very old method from some 17th, 18th century, where you measure the sample in the air, you same sample in water, and the difference from the Archimedes law. So the difference is the weight of the water, which was just pushed away. So if you know the density of water or of any liquid, let's say, so you can calculate the volume of the sample. This is a very nice method. The problematic thing is any porous material, because the porosity enables the liquids to come through, and then you have to decide the time of letting the sample being just saturated. It is quite tricky, so rather non-suitable for porous material. Then other possibility is the helium pycnometry, where you have two chambers. One is so-called reference chamber, and in one chamber you measure, you know volumes of the chambers, and one chamber there is inserted the object, the sample, and then you compare the presses P1 and P2. If the press of the helium increased, it means, or decreased, sorry, doesn't matter, increased, so it means that the volume of the sample increased, and so on. And so you can combine. This method is very accurate, but again, it is not quite suitable for porous material, because also helium is coming through the voids. And let's go on. This is the view of our hot lab, hot chamber. So let's go through the letters. Letter A signs the analytical scales, where we measure the sample either on air, either in water. So we are using the water pycnometry. When we come to letter B, so there is the two-chamber scale for helium pycnometry. What is necessary, especially for the water pycnometry, is some vacuum dryer it is necessary for some repeatability of the test. Yeah, because when we do one check of the density, it is not enough, so we have to dry it again, the sample, and repeat. It is quite time expensive process. Letter DE, those are the specimens which we test. On the bottom right-hand side picture, you can see our operator who manipulates with the manipulator in the or just in front of the cell. What is my major, my field of interest, is the mechanical properties change due to the radiation. Not only due to radiation, I can observe due to freeze thaw circumstance, due to higher temperature, due to mechanical damage, whatever. But recently I'm testing and we do the radiation-induced change. What I'd like to talk about is that the radiation expansion of the aggregates makes changes, and especially pressure inside the concrete, and there occur the cracks change the mechanical properties, and then we have to observe how much is the change, whether the strength and modulus of elasticity and other parameters are sufficient or not. So on the right-hand side picture, you can see what happens if there is a lot of neutrons coming through 1 quadrat centimeter. So that during about 30 years of operation of nuclear power plant, you reach 10 to 19 neutron per centimeter square, and within this number, let's say the mean value of all the tests of compressive strength is about 1. It means that test before irradiation and after irradiation is equal to 1. It's 100%. Nothing happens, plus minus. But after that, for example, in 40 years of operation, 60 years of operation of MPP, there is sudden decrease of all parameters. All these data, see on the picture, they come from the 1960s, 70s, 80s. Those are very old data. But recently, because we want to do LTO, we want to extend the lifetime of MPPs. So we are, say, repeating or prolonging the process and testing the samples of concrete again. Now you will see what happens with the tensile strength. It is very similar, but let's say the decrement of the tensile strength is even larger. So, for example, within 50 years of operation of MPP, you decrease 75%, so, which is very high. Somewhere in between, you can modulus of elasticity. Sorry. So as well, you can see the decrement is about 20–25%, rarely 50% of modulus. But this is the property which I am able to test by non-destructive testing. So I'm using non-destructive testing methods especially to test modulus of elasticity. I'm using some elastical waves, ultrasonic especially waves, through the material, and I'm able to observe the behavior of the material. I am testing linear or non-linear behavior. Usually when I'm using the linear material and linear methods, I'm using constant amplitudes, or I'm using constant frequencies. The opposite is nonlinear, because then I'm changing amplitudes, changing frequencies. Linear methods which we use and which we developed in CVR are ultrasonic pulse method and resonance method, impact echo. I'd like to introduce impact echo, which is part of resonance method. It says you impact to the tested sample and you have the answer, the echo. So in here you can see 3 cases. In the top screen you see picture number A, letter A, and we are trying to force the oscillation in flexion. So usually the peak on the spectrogram is the highest. So you can see the dependence of amplitude on frequency here. If we come to letter B, so we see the of longitudinal frequency, mostly because longitudinal velocity of longitudinal waves is the highest. So we are usually starting with this frequency measurement. When we use either letter A, either letter B, peak, we are able to calculate modulus of elasticity. On the other hand, there is letter C, and you can see torsion peak, and using torsion, you can either calculate shear modulus, which is quite usable, especially for some purposes. If you compare torsion and longitudinal, you can obtain Poisson ratio, which is nice for calculations and necessary for accurate calculation models of behavior and so on. Go on. So this is about the ultrasonic testing, where I'm showing 3 cases. So the letter A, the top picture, shows the dependence between amplitude and time. And it says when the sample is healthy, let's say non-damaged, so there is strong signal, high amplitude, and there is short time of the transmission. The time of transmission you can see on the left, and it is limited by the red color line. Number B, or letter B, shows the same sample. Oh, no, it's not the same, but it's from the same set of samples. And this sample is after gamma irradiation. It's about 2 megagrays. So you see that the time didn't change, not even the shape, the amplitude, the height of the amplitude didn't change. So that means that in this case, gamma irradiation didn't damage the sample. But when we put the samples after irradiation, we put the samples in a steam chamber, simulating the LOCA conditions. It means loss of coolant accident. So then suddenly you see a high decrement of amplitude and opposite increment of the time of transmission. It means that there are many voids and cracks, so that the signal has to go higher distance in not so good material, so it goes slower and the time is higher. To see what we were using, so on the top left-hand side picture, there are the samples prepared, inserting to the gamma chamber. On the left bottom picture, you can see the distribution of the temperatures in the samples. Mostly it is within ±2 degrees of centigrade, Celsius. On the right top right hand picture, you can see view to the LOCA chamber, where we simulate the LOCA conditions, and we can have very fast increment of the temperature and pressure. In this case, we increased the temperature about 250 degrees Celsius in a few seconds. You can see on the bottom right hand picture, and the pressure was increased to approximately 9 bars. Yes, so after this treatment, our samples got damaged, and it was damaged by several tenths of %. What I'd like to show is the hot cell, where we have letter A. This is our non-destructive testing tool, which is manipulator targeted for pulse method in the ultrasonic. Letter B, so there you can see hydraulic press, and there are some small tools, maybe not so much visible, but there are tools for E-modulus testing. Also, we can test splitting strength, but it's not visible in picture. So let's go on and talk about nonlinear methods. There are two methods which we developed. Especially it was wave modulation spectroscopy and nonlinear resonance ultrasonic spectroscopy. When I'm talking about nonlinear, targeting to the plastic material properties, because linear method and linear behavior goes with elastic property. So this is one situation where we used our nonlinear spectroscopy manipulator Horimier, and we are trying to test the reactor shielding. It was in Řeš about 2 years ago. We developed manipulator Horimier, which you can see on the right hand picture, and a set of instruments and amplifiers and whatever seen on the left hand side picture. This picture says which is the difference between healthy and damaged concrete. Healthy is upstairs, damaged is downstairs. This is the let's say this is graph where you see amplitude and frequency. So two signals which emits other and other signals, and especially interested in F1 plus F2 signal frequency, where I measure the amplitudes, compare those, and measure the beta coefficient. Healthy sample, you can see beta equals 1/100 of volts minus 1, and damaged sample is 7 volts minus 1. I will show you what happens. So in here you can see graph, which is the stress strain diagram. There is stress on the vertical and strain on the horizontal axis. The higher is parameter beta, the bigger is the nonlinearity. So linear material, beta would be very, very small. In this case, smaller than 0.4004. The opposite, when the material is very, very much damaged, beta parameter is much, much higher, so that it doesn't behave elastically, but plastically. But which I'd like to show is the NRAS, ultrasonic spectroscopy. It's working so that I'm increasing amplitude, and I will finish. I'm increasing amplitude, and the frequency shifts to the left side when the sample is damaged. On the bottom, you can see comparison between various methods. When I'm doing bending test, so the samples without damage, the strength is high. When I damage the sample, strength is low. The method NRAS, when I damage the samples, the parameter is very low, and nonlinear wave modulation spectroscopy parameter beta, again, when I damage the sample, the parameter is very low. I'm not sure. So let's go on. What is our work? Current and future. So we started in the project SUSEN. We continued by research for SUSEN. We developed methods NWMS, then the ultrasonic pulse method, and NRAS. We continued by the Scheller way. We also had a project internal IPNOP for concrete testing, which is very we just succeeded. I'm sorry again. Then we recently finished project Betony MVČR of Ministry of Interior. It was also successful. What we started to do is irradiation and post-irradiation examination of aggregates. It was in 2018. From last year, we got also Betony MVČR number 2 of Ministry of Interior project. We developed again manipulator, and we developed that methodology. Also last year we started Horizon 2020 project URAT. This year we are starting Horizon 2020 project ACES, targeted for irradiation of concrete again. And also this year we started some commercial product irradiation of concrete and post-irradiation examination. So this is all. I'm very sorry I extended the time, and that's it. Thank you for listening.
Okay, thank you very much to our presenter, to Zbigniew. Yeah, it was again some interesting work. We moved from nanoworld, from uranium particles to concrete testing and non-destructive testing. So very interesting, and we will continue with this area. And another presenter is Jan Patera, who will tell you something about the principles of inspection procedure for 3D measurement in current power plants. So, Jan, if you hear us, please, place is yours. So.
I don't know if you can see my screen just now or not.
Not yet.
Not yet.
But we can hear you. That's perfect. Thank you.
Okay.
Hello.
Great. And now?
Wonderful. Yes.
Yeah. Okay. Thank you. So, good afternoon, ladies and gentlemen. Good evening to Japan. My name is Jan Patera, and I will tell you something about the topic that had to be presented by our colleague Jaroslav Brom, but he's ill for some time, so I will do it instead. So I will tell you something about principles of inspection procedure for 3D measurements in nuclear power plants. So it's basically about inspection procedure, which was developed within the project Research for SUSEN, and it is also a result of the Research for SUSEN project used many times at nuclear power plants. So today I will focus on some history and motivation of 3D measurements in nuclear power plants. I will tell you about most commonly used measuring equipment, impact of our experience, what we learned, and at the end I will show you some examples of 3D scanning in power plants. So basically 3D measurements in nuclear power plants are a part of in-service inspections during outages since 2017. Our first measurement was in 2017, the main dividing plane in Temelin nuclear power plant that you can see in the picture. This measurement was quite successful, but from today's point of view, it was quite inaccurate, which means that it was far from the measuring accuracy of the 3D scanner in the lab. So we had to solve various problems, which in fact are today parts of the inspection procedure. About the motivation, why we have to use or why we would like to use 3D scanning in nuclear power plants. One of the advantages is that it helps to reduce human error, both during measurement and assessment. And second is that we can compare our measurement with future measurements. So basically we can work with scanned data from all outages at once. And what we usually look for are some kind of geometric changes like wear or corrosion pits. Some words on measuring equipment. The most commonly used measuring device is the device you can see on the right, which is called hexagon roller arm with RS4 laser scanner. It consists of two parts. One is a measuring arm, and at its end there is something that looks like a pistol, which is a laser scanner. Well, it has quite high acquisition rate, about 700,000 points per second. And maybe the most important parameter is standoff distance, which means this is the distance we have to keep from the scanned surface, which is about 16 centimeters. And there are some other parameters like point spacing, which means this is spacing of 2 points in a grid we scan, which is about 11 microns, and accuracy of each these points are about 28 micrometers. In the next slides, I will show you some impacts on the inspection procedure from various points of view. I will start with the point of view of the measuring equipment, because in the nuclear power plant there are many dimensional and spatial constraints, because there is not a lot of space usually, and from this region it is usually good to use laser arm scanners, because they have a relatively small standoff distance, and it can also scan very reflexive surfaces. So, but sometimes there is also a problem with space. So our inspection procedure requires us to make a replica of surface we cannot scan. This is one constraint, and the other constraint or other group of constraints are mounting constraints, which means that the measuring device must be stable during measurement. For example, it must be attached by magnets, but usually we cannot use magnets, so we have to use some specially made fixture. For example, or an example you can see in the picture on the right, where there is a solid tripod, a three-sided steel plate standing on 3 screws that we used for scanning of main demanding plane. Another point of view is point of view of expected imperfections, because there is some accuracy of the scanner, but of the measuring device, but its accuracy is mostly achievable in ideal laboratory conditions, which is not true for all cases, because, for example, when we scan reactor lid, the accuracy is the same as in the lab, but mostly it is not achievable in situ. So basically, our inspection procedure requires us to make a checking replica of the surface to verify the accuracy of real measurements. There is also some criterion for the difference between replica and 3D scan, but basically this replica helps us to increase accuracy of the 3D scanning. Point of view of radiation environment. Inspection procedure requires to reduce possibility of surface contamination. Basically, we have to eliminate all possible cables, and the other cables we have to wrap in the yellow plastic cover. When there is a high surface contamination, we have to wrap also the measuring device, as you can see in the picture on the right. And we also have to use plastic cover for storage space, like if you look on the picture on the bottom, there is a laptop on that plastic cover, and 2 guys scanning, and the left one is probably me. Point of view of calibration or verification. So there is a requirement of calibration before each measurement. This calibration is performed on 800 millimeter long checking rod that you can see on a picture. There is also some kind of difference, but this is not so important. There is also a requirement of shocks to be recorded, because these shocks may affect accuracy, and these shocks are recorded by a simple accelerometer. And in case of shock, we have to calibrate or do calibration also after each measurement. The last part of these point of views are impacts resulting from data processing requirements. Usually, these requirements are defined by our customer, but usually we assess corrosion pits greater than some value or geometric changes between outages. Some applications require us to use microscripts, which are powerful tools for assessment because they still assess the same way. They allow also fast data processing and allow also transition from point assessment to continuous assessment. Now, in the last slides, I will show you some examples of 3D scanning in nuclear power plants. The first example is scanning of main dividing plane and reactor lid. The both you can see in the picture on the top right. And this is an example of a continuous assessment where we measure seal bruises in grooves and surrounding defects. There is a nickel sealing in the groove, so our measurement is important for determining the size of the nickel sealing. In the graph below, you can see some kind of continuous results of the bruise depth around the circumference. Another example of 3D scanning are steam generator pipelines, which are located next to steam generator. There are many corrosion pits from which a crack may initiate, and this application is also assessed automatically, which means that it automatically looks for the largest corrosion pits and their position. And it also automatically generates some kind of list that you can see here. Another example is super emergency feedwater nozzle, which is located on the steam generator in Dukovany nuclear power plant. And in this case, we had to scan exact geometry for weld overlay qualification. In this application, we had to measure pressurizer main safety valve seal. In fact, it was 24 newly delivered pieces where we measured roundness, coaxiality, and thickness, and everything was automatically assessed. And a very specific application was scanning of corrosion pits in wet spent fuel storage in Řeš. because of the poor access, we first had made some replicas of corrosion pits, and then we scanned them. And the assessment was much more accurate from a point of view than the previous one that was done by microscopes. And we are approaching the end of my presentation. So I will say again that this inspection procedure for 3D measurements in nuclear power plants was developed within the project Research for SUSEN. It was a result of the Research for SUSEN project, and it has been used many times at nuclear power plants. Among its benefits, there are more accurate and comparable results, lifetime monitoring and trend prediction. This inspection procedure complements existing methods, and it allows for faster data processing and increases safety of measuring equipment. So thank you for your attention, and if you have any questions.
Thank you, Jan. Thanks a lot for your presentation. We give some minutes to our colleagues or to our audience for the questions. And in the meantime, if there is still Zbigněk Hlaváč between presenters, there was one question for you. Are you there, Zbigněk? Probably he's already. Zbigněk? No. Okay, never mind. We definitely make sure that all the questions which were not or could not be answered will be sent to our presenters. So, okay. According to the schedule, there shall be the last guest presentation from Japan, Professor Maruyama from Nagoya University. Unfortunately, we still don't have connection with him by email. We could communicate, but there is some issue with connecting. So if we can wait a few minutes, otherwise, yeah. So we try to contact him and continue.
So Jana, here's me, Zbigněk. What was the
Zbigněk, excellent. So perfect. So we can fill the time. Okay, question. I don't know if you could see it on the chat. If not, I will read it for you. So, can you describe a little bit more about temperature distribution, measurement, and calculation during irradiation in gamma chamber?
Thank you for this question. Maybe I think I don't have any nice picture. So the calculation was done such or so that we took the distance from the source of irradiation from the cobalt-60. Then we did or calculated what is the power forced in the sample specific, and the power we gave to our table guy who calculated, and I think he was Karel Gregor, who is not working there anymore. And so using mechanical properties or physical properties of the material and the power, we are able to estimate the temperature. It was very important to put there also information about ventilation or air conditions, because the values changed a lot when I put there some small wind, I don't know, 20 meters per second. So it was cooled a lot when we did the modeling. but we did measurement of the temperature, and the temperature it was done using thermocouples, and we put thermocouples in various samples in various positions. Also, we did some kind of reference sample which was sealed by very, very thick isolation, and it was just confirmed that the variation of temperatures would be higher than about 1-2 degrees of Celsius. Afraid of very high gamma source and gamma heating, but it was not there. Our source of gamma, well, it had activity, the nominal activity about 20 terabecquerels. I'm sorry, 200 terabecquerels. Recently, it is about 120 because it's much older now. So if this is all for the question and the answer. If you don't mind, I can show the measurement when we did the thermocouple measurement.
Okay. Yeah, we are here still solving the problem with the connection with our guest from Japan. It will be great if you want to show the measurement, Zbigniew, yeah, to continue with your explanation of the question. So yeah, you can. And otherwise, we definitely will wait for a next presenter afterwards. So please show the measurement. Yeah, thanks.
So it is described only in Czech language. Nevertheless, there are the samples. It is 4 × 4 centimeters, 16 centimeters long. Then, especially this screen shows the temperatures distribution without the source. The source was downstairs inside the concrete. But then, if I show another screen, only when occurs the source, the temperature in the samples inside increased by about 2 centigrades. To differentiate when we put there some air conditioner, yeah, because sometimes we need to take off the ozone which occurs after irradiation. So we have to condition the air. So this is the difference before and after. There on the very right hand side, you can see degree 13.3 degrees Celsius. It is in the sealed sample. Yeah, so sealed and unsealed can be 3 degrees variation, and it was very highly sealed. This screen shows what happens when there is the conditioner, there is the wind. So again, there is 1/10 of Celsius degrees of decrement when I put there some air conditioner. So that's it. Okay. Thank you very much. Thanks for all the also visual explanation. We really appreciate that, Zbigniew. Since we are in the stage, we still don't have Professor Mariama, we decided to make a break, so you have more time to have some coffee, and we will start again at 1 o'clock with presentation of Lukáš Košek to keep the schedule. So at 1 o'clock we will be back with our 4th session of our conference. So thank you for understanding. So hello, welcome back. Good afternoon or noon.
we are here about to start our last session of conference SUSEN 2020. We would like to welcome here Lukáš Košek, our colleague, who will tell you something about the performance of structural materials in heavy liquid metals. As you know, is part of the research on generation 4 nuclear reactors. So, and him and his group is heavily involved in this research. So, Lukáš, the floor is yours.
Good afternoon. I'm Lukáš Košek and I will show you some results of corrosion test in heavy liquid metals that we done here in Řeš in frame of SUSEN project and GEMA project. I will start with why we need a new type of reactors at all. Then I will discuss the corrosion in heavy liquid metals, what kind of materials we will use for this type of reactor, what mitigation strategies are used in heavy liquid metals, and I will show you some metallography results of corrosion tests. And there are, of course, some open questions and conclusion. So let's start why we need new reactors. I was looking for one slide that will show us necessity to change the reactor technology, and I found it in some OECD study from 2013, where is a nice chart showing us that if we want to keep 20% of energy production from nuclear with growing demand that is expected in developing countries, that uranium will be used or utilized completely around 2100 if we will not deploy fast breeder reactors. So this chart is something like 20% world demand supply. So it's not very radical scenario, is just what we have today, but growing demand in Latin America or South Africa or Asia requires some change from EVR technology with limited plutonium recycling. Why we want to cool them by heavy liquid metals? From my point of view, is perfect coolant, especially from safety, because they are very high boiling point, so you don't need pressure vessel. It's low reactivity in comparison with sodium. They have also some benefits for reactor physics. They are poor moderators, so you can have a very hard, fast spectrum for and high breeding ratios. They are self-shielding. They can be recycled. So if they are perfect, why we don't have some reactors? There is lots of small reactors or medium range planned. Even companies as Westinghouse are planning deploy around 2040 some reactors. So it's quite exciting technology. It's almost available to use, except the material problems. So we are focused on materials. I picked one. It's Alfred European reactor demonstrator. It's quite conservative because we plan to use already available materials So temperature is limited to something like 480 degrees C, with maximum temperatures on cladding 550 or 600 during some accident on transient state. Neutron irradiation for components should be limited to 2 dPa and are expected for 100 dPa. So message here is technology is ready, we just need some materials. Reference materials for this reactor is 316L for vessel, primary pumps, steam generators. It's classical steel for nuclear energetics. It's well known and lots of data is already available. But it has a problem with radiation-induced swelling and hardening. For cladding, there is a candidate steel developed for sodium fast reactor. It's 1515 titanium. It has precipitation type of steel. It's good irradiation properties in comparison with the 16L. There is also grade 91 ferritic steel. It was developed originally for a fast breeder, but now it's extensively used in fossil plants. It has unique microstructure that makes it very high temperature and creep resistant, but it's very difficult to use because it requires precise post-build heat treatment. And also there is a Eurofer steel that is not developed for fission reactors, but was developed for a demo plant for fusion, with the benefit of being low activated. So as researchers, we decided to test it as well, but it's not Alfred or Miraha type steel. So problem with corrosion is based on solubility of elements of mainly nickel. If you can see here, for example, sodium is virtually non-corrosive for stainless steels because there is very low solubility of all alloying elements. But on the other hand, heavy liquid metals, it's a completely different picture, especially for lead bismuth eutectics. That is highly corrosive, and we had to limit the temperature. And the situation with lead is 10 times better, I would say. So mitigation strategies for LFR. Right now is available oxygen control. It's kind of balance between high temperature oxidation and dissolution. In presence of oxygen, we can grow up some FLCR spinel that prevents nickel leaching out. This strategy works till 480 degrees C, but at higher temperatures, the dissolution takes over and we can see some localized attacks. Short term means that it's available right now, but not at industrial scale. So this strategy is based on coatings of known materials. That has one problem, because it's hard to guarantee perfect coating over whole surface. Even small defect can cause localized attack that is really problematic, for example, on fuel claddings. In the long term, we can develop some aluminum or silicon enriched steels that have high corrosion resistance up to like 600, 700, even more degrees C, but it's a long-term process with all qualification and irradiation It's estimated to something like 20 years. Therefore, for Alfred, we plan this oxygen control method with possible some coatings. Effect of oxygen can be demonstrated on this on these pictures. On the left, there is virtually no oxygen, so there is no stable oxide forming in these conditions. And you can see that after 1000 hours, nickel is leached out in unacceptable manner. And even if this is very high temperature for stainless steel, with some oxygen, you can develop some oxide barrier that prevents this to happen. Okay, so for some flow test, we build up loop. We call it MATLU, it's Material Research Loop. That has, it's non-isothermal, so it has cold leg on the left. There is a pump and filter, and on the right there is two parallel corrosion sections where there is narrow channels with specimens. There are cylindrical specimens of 10 millimeters diameter, and we can reach there 3 meters per second. So some results. These specimens were exposed for 8,000 hours in controlled lead with oxygen level 1 to -7 weight%. It's something like 400 milligrams in the loop. Oh, micrograms, sorry. Difference between austenitic and ferritic steel is that austenitic steels cover themselves with extremely thin layer that is barely visible. On the other hand, the grade 91 steel grows very thick magnetite layer that is somehow protects it. This key difference. Over the time, the evolution is that stainless steel forms a few hundred millimeters thin, nanometers thin layer that after 2000 to 4000 hours starts peeling off. It's challenging for analysis because it's extremely thin. So we use some X-ray diffraction, and the preliminary results show that it's obviously there's magnetite, some chromium oxides, but also surprising is nickel. Nickel oxide is involved. It's quite interesting since oxygen level is lower than its stability than is needed for stable nickel oxide. But in this spinel, it's not a problem, so it's quite nice result here. There are some differences between stainless steels. For example, IC 321 showed such consistent behavior that completely surprised us that it's behaving much better than 316L steel. Even after 8,000 hours, there is still no oxidation, and this very thin layer is stable. It's quite interesting. On the other hand, the lower content of chromium in 1515 titanium leads to some magnetite growth and some localized oxidation attack. What is very important that there is no dissolution of nickel and penetration of lead. That was observed on 316H. That's only steel that has such behavior in our test, and it's really hard to find some explanation for this behavior. So we try to remove some machining deformation after fine turning by mechanical and electropolishing to see what's happened. And the result was quite interesting because the electropolished sample was attacked on brain boundaries by a lead that is not seen on some mechanical fine-turned specimens, for example. So the surface finish is definitely a thing that needs more study. So some comparison of ferritic steels here. Interesting is that in theory the ferritic steel grows spinel and magnetite on top, and usually is covered completely. In our case, because of machining of our specimen, there are some grooves that were never covered by magnetite. It was a surprising result and really needs to be more investigated. While Eurofer is completely oxidized on a whole surface, you can see the typical features there: internal oxidation, then there is a spinel and magnetite on top. This is visible also on distribution of oxide thickness, that after 8,000 hours, the Eurofer has normal distribution, but T91, especially this 8,000 specimen, is 50% uncovered by oxide. So we took a closer look on this specimen, and you can see that in chemical composition there is no difference. There is a cross-section between the unattacked place and a place where is magnetite developed, and only difference is fine grain and heavily modified grain structure, but there is no difference in chemical composition. So if we take a look on how fast is material lost, there are two theories for that. Normal is a parabolic rate that you grow up some oxide that is increasing its thickness in time and slowing the diffusion processes. If you integrate this, you can get this parabolic law. But our data is impossible fit with this type of law, so it's more like logarithmic law. That has some explanation for extremely thin layers in orders of nanometers that lies in quantum mechanics, but it's definitely not our case. So it's maybe a combination of parabolic law at the beginning and some peeling of the magnetite that may appear in that way, but I have not enough points for that. So we have some open questions. Why is here not uniform behavior of T91? That's first unknown here. Effect of surface treatment. If we found that this fine grain caused by machining or modified surface layer will be used as surface finish, how long it takes? If it's maybe just temporary thing for 10,000 hours, we don't know it. Second thing is, can we use polishing as accelerated corrosion tests? Because the corrosion tests are very long and expensive. So it will be nice to have something how to speed it up. Also, the effect of higher flow is unknown at this moment, because we calculated with Sigma company that impeller pump will operate something like 13 to 17 meters per second of relative speed between blades and the liquid lead. So it's completely unknown, the behavior of this material in this regime. Also, there are some questions connected to lost material in circuit. It's because the oxide layers are peeling off and make it impure, and that is question now what's happened there. If they affect the oxygen sensor measurements, for example, it will be very its impact for safety operation here, or can be abrasive for components of how this deposition process will happen. It's not very well studied, so these are still open questions. We can draw some conclusions that liquid lead is less corrosive to austenitic steels than lead bismuth alloy that's usually studied. Some our fine-turned specimens of austenitic steel, except 316H, haven't shown any sign of dissolution attack of nickel over 8,000 hours. We observe intergranular dissolution attack on polished specimens even from 1,000 hours. So I think it's it's necessary to study the surface treatment expected in industrial processes for each component. Also, surprise was that IC321 showed very nice corrosion behavior that we didn't expect. 1515 titanium and 316L develop some oxide layer that starts peeling off after 4,000 hours. But what happened after is unknown, and I'm not sure if our goal is to reach 16,000 hours. If 16,000 hours is enough to show us some reasonable corrosion, it's quite still open question. Interesting is also the slow oxidation rate of T91, and why is 50% of specimen uncovered with protection or magnetite is also very interesting. So thank you for attention. I hope it will interest you this topic.
Okay. Thank you, Lukáš, for your presentation. Thanks a lot. It was a very interesting excursion to material science and corrosion in heavy liquid metals, which are one of the coolants for the advanced reactor of generation 4. I think we could see or hear that there is the good news about the corrosion results, but another part of this research is definitely has to be underlined, that a lot of questions and a lot of studies should be still done to answer all. I think that we know that to select proper materials is one thing, and but the topic is continuing with the licensing and validating and so on. So this is our lab involved in and working on that together with also, as you can see, in the project with other European institutes, and also this already mentioned our first presenter, Lorenzo Malerba. So there's the European effort towards materials for the advanced nuclear power plants. So I have for you news. Our guest presenter from Japan, who could not attend in his time box, will is still available to actually present in the end of this presentation, because we would like to continue with the schedule as it is. So there will be 2 presentations from our colleagues from CVR, and then at 14:10, when it's schedule at the end, please don't switch off. There will be last but not least perfect presentation of the Professor Mariam, and he will be talking about the national Japanese research on concrete degradation under neutron and gamma irradiation environments. So this will be at 2 o'clock, 10 minutes of our time. So, but now we continue as the schedule is for the section 4 with our colleague Evgen Novak. And from material research, now we are going to neutron physics and a lot of interesting stuff. His presentation calculated and measured spectra of 14. Okay, Evgen is already there, and he will tell you.
Chat. Yes, I am online. Hello, everybody. I'd like to say hello to one lady presented here in online, and other around 80 or 90 people watching us through the web. So there is my presentation. Not yet. Okay, presentation mode. Okay, so my name is Evgen Novak. I'm a deputy of the big group of the people focusing in our institute in our department for the experimental reactor and other physics, which is a very important part or section of the nuclear data validation. As among all the material contributions we have heard during our conference, so there is a single description of our neutron source we had got to, for the SUSEN project, which is a 14 MeV neutron generation. As you see, 14 MeV, it is a connect with this fusion experiments. What we should see today, so is some description why we are doing such research or such experiment. What is in fact the operation, how operate the neutron generator we have, what does it mean have a benchmark, material experiments, and some other discussion what we have done until now. Neutron generator we got from the Gradle company, which is located in Luxembourg, and it was acquired by the SUSEN project, and is already operated several years. At the present time, we are focused for the calculated and experiment data comparison, which is the most important part of all the project. At the beginning, you need to have a model prepared before you start to any material research. Then you have to verify the model. You have to have equipment which should be verified in the real field, in reactor or in the neutron sources, and then you can continue with the material research. The comparison of calculation or of the model and experiment is a task of our group. Here. So there is our baby 14 MeV reactor. Some main parameters to be oriented, how what are the dimensions. The length of the neutron tube is around 130 centimeters, diameters around 15-16 centimeters. There is a lead cover with a thickness of 1 centimeter to mitigate or to dump gamma rays coming also from the tube. Inside the tube, which will be discussed in more details later, is a reaction chamber, reaction volume with the length of the 35 centimeter with diameter around 10 centimeter, and there is a place where the reaction starts. We can produce at the maximum power, which was intended about 24 kilowatts, with a high voltage of 160 kilovolts and undercurrent around 120 milliamps. So it should produce 1 power 10 neutrons per second, which is a very strong source. Unfortunately, due to the operation, we had faced some technological troubles with the producer, and we had some damaging in the high voltage part, and after repair, we can operate it a little bit on the less power, but still it is possible to use such generator for our experiment. There is a promise of how does it operate. So in the reaction chamber, which is a cylindrical, which has a cylindrical shape, we release from the getter, which is a storage of the deuterium, is a release to the volume and exceed the deuterium and tritium ions are accelerated toward the cathode, and then the cathode is a semi-transparent. The principle of operation you see here, so the ions are coming through the cathode, come through this cathode and oscillate in the field. Some of them are trapped inside the cathode and creates a virtual anode. And the ions of deuterium and tritium are trapped inside and form quasi-solid target. Other ions coming from the volume are attacking or react with the ions trapped inside and producing the 14 MeV neutrons. The animation taken from the Gradle pages or Gradle webs is here. The first part is the oscillating of the ions, deuterium or tritium, and there is we have an interaction here and producing neutrons. For the experiment, for the measurement and validation data, we need several sources. Each source using in our department has a different, or in an institution we are cooperate, has a different energy. So we had used for validation of our, or checking of our spectrometer, we had used the neutron source, also the small neutron generator, but opposite our that has a gas filling. It small generator in Technical University Ostrava. It has a solid target with the tritium. Then we use the isotopic neutron source with average energy around 2.5 or 2.4 MeV, comparable with the uranium fission spectrum. And last source is 18 MeV accelerator. So we have a very long range of the energies that could be measured by our spectrometer based with Stillben detector. How we perform the measurement. So we have two ways. at the beginning using the neutron source based on isotopic californium, which is quite small, as you see at the previews. This is in scale, so it's around 3 centimeters in length and 1.5 centimeter in width. Diameter. There is a small amount of californium, produce 0.1 power 9 neutrons per second. It is transported to the middle of some material assembly, which could be cube, could in the ideal case could be the sphere or some slab. Then we measure using the detector the leakage spectra. Of course, neutron generator is much bigger equipment, so we cannot put it inside any assembly. So the measurement in the case of the neutron generators also measurement leakage spectra, but behind the slabs of any materials. The basic principle of the measurement performed in our laboratories is described in the second picture on the right side. This is the case of the sphere with diameter of the pure iron with diameter 100 centimeter. Inside there is the isotopic neutron source, and you see something like cones here. Why we do this way? Because so for each measurement we have to perform in 2 steps. One is a measurement without this shielding cone. So we measure everything, all the signal, useful signal from the assembly, scattering of the air, floor, other sources placed in the laboratory of the walls. Then, second measurement, we put between or among the detector, between the detector and assembly, we put shielding cone, which shield the useful signal, and then, as is written here, we subtract both the information and we will get a pure signal. Of course, it pushes special stress for the quality of the equipment, long-term stability. But because we have, let's say, 30 or 40 years experience with it, so we can guarantee that the procedure is all the time okay. There is a maybe big, maybe small fleet of our benchmark assemblies on which during the last year was tested the spectrometer and also the validation experiments or comparison of experimental and model data were tested. On the left side, you see the 50 centimeter iron sphere, which is a, let's say, world standard for such leakage spectra measurement. We have nickel sphere with of 50 diameters, some assemblies on the graphite, stainless steel, and I skip these 2. I will explain later. And also we have the biggest iron sphere in the Europe with a diameter of 100 centimeter. The assemblies from iron, from lead and cuprum are intend to be measured like a part of the construction material for the fusion facility as a first wall in the plasma chamber. So again, the experiment that we perform here are focused on the comparison, calculated and experiment data. There you see the real measurement in our laboratory with the californium source and the several type of the detectors with the steel band that measure measures in the energy range from 1 MeV or less, a little bit less than 1 MeV until 20 MeV. We have also propulsion counter filled by hydrogen, spherical detector that measure from the some trailmar on 20 keV until 1 MeV. There is an example measurement with the conus. Over there, this is a measurement without conus. For such measurement, it's important to place, to mitigate effect of the reflect neutrons or reflect rays of the walls. So we standardly place such assemblies in the height of the 2 meters above the floor. You can imagine it's a not easy task because the mass or the weight of such assembly, as you see here, is about 2,000 kilograms. And materials of the support should not affect our measurement. So it is made from dural, which is almost transparent for neutrons. How was our measurement of the single neutron sources? At first, there is a result of measurement of the facility of the PET center. We had to place the detector near beam and measure leakage spectra in a different angles and compare the calculation with experiment. The calculation was performed with different MCNP codes, 6.1 and 6G, and you see there is some discrepancies between experiment and measurement. And of course, we should evaluate why is the reason and if the nuclear data library used for calculation are proper for such purpose or should be changed or a little bit slightly make in some energy range some differences or correction for these nuclear libraries. Second measurement we had performed in Ostrava, in Technical University Ostrava. That the small neutron generator was located under Earth, about 10 meters under Earth, again with the concrete shielding, and we had measured the leakage spectra in different angles around the neutron generator and compare with our calculation. In this case, we used the still band spectrometer, and the data, the result, it means energy shift in the spectrum of the 14 MeV peak was confirmed by the with measurement by diamond detector. So this is the second step. We have validated we have tested our spectrometry equipment on different unknown source and let's say validate it with or verify is by different spectrometer. Last measurement we had performed was in at our neutron generator. What was interesting, let's say unexpected, was that the peak of the 14 MeV was doubled. At first we saw that is the reason is some problems with the resonance, reflection, cables, electronics, but after we had got confirmation by diamond detector, we found that the peak is doubled due to the geometry and the way of the reaction inside the neutron generator. The maxima in the two cases differ because in the first case, the incident particle hits the stationary particle inside the virtual anode. while in the second case, the incident particle hits a particle with similar energy but opposite momentum. So the peak is always during the measurement in the perpendicular position is always doubled. But for the experiment and for our measurement has not played significant role if we know what is inside, which is the input spectrum. We can then describe what is the what is caused by the material, and we can measure the leakage spectra. Description by some model, by some program. So in the case of our generator, it was very complicated. As you see, of course, each producer covers his copyrights and provide us with not completely perfect data for description. So during of the neutron generator and to model to prepare computation or model for the calculation as much as possible similar to the reality. Is it impossible, as I see from the business secret or industrial secret, to model in details? So we have to simplify again the model here of the generator, and then for the calculation we use the giant code, because MCNP code is impossible to use for model behavior in the gas or the mixture of the deuterium and tritium. As you see the small boy here, so it's very difficult to make a model real or close to reality. What is the time? Yeah, 32 minutes. Okay, this is the last 3 slides. There is a result of our spectra modeling. As you see, we got in the there is several detectors modeled by the giant code. In the middle or in the perpendicular direction, we got the same shape of the spectrum, which confirmed our measurement. That's perfect, that's fine. So we finally have a tool for modeling of the spectra and compares the experiments. Now, at the present time, are coming the experiment with the neutron flux distribution, ovality, let's say radial distribution. We got difference around 5% plus minus, so which is perfect. That's almost perfect, and interesting distribution with at the axial direction. 2 days ago, we had prepared experiment with more active foils. It's based on the gamma evaluation of activated Teflon foils, the reaction on the fluor, and later producing the annihilation peak, and the flat or area around the peak is proportional to the energy or the flux intensity. And since this morning, we have the first have a result. Interesting that the middle part of the 35 long reaction chamber, we have almost, let's say, beam, which is perfect because we will not get much scattering of the wall and floor. There is another experiment prepared for next week, so we will continue with mapping. And then after that, we will ready for the measurement real assemblies for project, where we participate or where we play some important roles with our neutron generator. It is we collaborate with the Eurofusion Consortium and with our group of the VC water-cooled lithium loop of our company. There we are responsible for neutronics benchmark experiment. Although we were invited to measure in a Frascati neutron generator in Italy, unfortunately, due to the COVID, we had 1 year delay, so this measurement will be prepared for the next year. And although we participate in some nuclear data measurement, it means verification of the nuclear data by experiment. There is an assembly of in Frascati where we should perform measurement on VCEL mockup. It means one scale, 1-to-1 scale. Again, as you see, is in the height of the 2 meters, so is a, let's say, is a challenge for us to have equipment here and to perform all the measurement. Some references you can see later, and there is an acknowledgement again for support in the frame of the project, and my thanks for your attention. Thank you very much. And of course, if you have any questions, you can put it now or later send us by mail.
Okay, thank you very much, Evgen. Thanks a lot for your presentation. Since there is no question and we are quite fine on time, so I would like to invite to speak our last presenter in this session 4, but not last in all conference. I already announced you that we will have one more presentation after this one. So, but for this moment, we have again our remote colleague from Plzeň, so remotely connected, I wanted to say, but he's also in CVR. Working with the group of people related or studying or investigating actually fusion technology. So you have nice mix of topics what we are doing here in CVR. So I see that Tomáš is already on. Hello, Tomáš. Welcome to our session, and we are happy to hear and see you and hear you talking about our high heat flux test facility, Helča. So, hello.
Hello. Thank you for the introduction. I will share my screen.
Tomáš, if I may interrupt before you start, I don't know, there is a lot of noise from your room, so if you have some chatty colleagues, please, if you can mute them, thank you. Not yourself, not the computer, just the colleagues, thank you. Okay.
Well, is that better?
It's better, yes. Thank you very much. Okay.
Can you see the screen?
We can see your presentation. Yeah.
Perfect. So, good afternoon or good evening to those in a different time zone. My name is Tomáš Kubásek. I'm a junior researcher here at CVR. And I will tell you something about Helča, our high heat flux device. I was supposed to be joined by my colleague Richard, but he had more important engagements. For those who don't know, we are located in Plzeň, unlike most of CVR. This is our experimental facility. It looks big, but Helča doesn't take all of it. Most of it only most of it is only in this middle building. Here is a look inside. This is an earlier model, which Helcha in the past year has undergone some very extensive improvements and expansions. But here you can see the basis of our facility. Helcha is here. You will see a better picture in a moment. And here you can see, for example, the cooling system that is cooling our samples. And here is the control room from which we can see almost everything. And I'm located here right now as I speak. This is the current layout or our floor plan. Like I said, in the past year, there's been some major improvements. So all these colored rectangles are new stainless steel rooms that have been built due to the nature of the testing that we are going to conduct, mainly for health and safety reasons. I will tell you why in a moment as well. I will describe this picture later in the presentation. Here you can see Helcha in her full glory. It is basically a stainless steel vacuum vessel equipped with an electron beam gun. The vessel is 2.5 meters in diameter and 2.5 meters lengthwise, to give you an idea of the size. Here we have 2 mechanical pumps for reaching medium vacuum and 2 cryo pumps on either side to reach a high vacuum of up to 10 to the power of -4 pascals. What is also important in this picture is this lid, which is retractable. You can see this in the photograph on the left. Basically, we remove the lid, install a sample onto this holder, which is then connected to the cooling system by these pipes. That is then closed. The whole vessel is evacuated, and we can irradiate the sample with the electron beam gun. What exactly is Helcha? Helcha stands for High Energy Load Check Assembly, which basically means it is used for testing by applying a high energy load. In other words, high heat flux testing, as was the title of this presentation. Our electron beam gun can provide up to 800 kilowatts of power using an acceleration voltage of 55 kilovolts. And this facility was primarily built to test plasma-facing components of fusion reactors. Mainly first wall components, which I will talk about later. Here you have some specifications. I forgot to mention that the lid is equipped with a kinematic system, which can rotate and tilt the sample as we like, because the first wall components, they are not all flat surfaces. They have some angles, so we need to be able to test different angles. Yes, an important part is the cooling system, because the sample will get very hot, so we need a proper cooling system. We are using the demineralized water, which we create here at the facility ourselves. Our facility can provide temperatures from room temperature up to 320 degrees Celsius and a pressure of 150 megapascals or 150 atmospheres. and a flow rate of 40 cubic meters per hour through the sample. Here are some specifications of the electron beam gun. Like I said, what I didn't mention is why we can reach a high vacuum of, I said, 10 to the -4 pascals. Our operating pressure is actually higher. We reached it by introducing nitrogen gas. We use nitrogen because it is relatively inert. It is easy to obtain, and it is not as easy to ionize as, let's say, argon or other noble gases. So there is less danger of sputtering the cathode of the electron beam gun. Excuse me. Here is the backside of Helcha. If I scroll back, which is from this side, you can see it in this picture. But here is all the important diagnostic equipment. In the middle is the electron beam gun, which is omitted here. And we have a lot of cameras. We have high-resolution visible cameras, then 4 pyrometers. But most importantly, we have 4 infrared cameras, 2 for long wavelengths and 2 for medium wavelengths, and an X-ray camera, which we use to analyze the uniformity of irradiation of the sample. Here are some specifications if you'd like to read them. So, like I said, Helcha was primarily built to test plasma-phasing components. At the moment, we have 2 major contracts. First one is Fusion for Energy, which is the European branch of ITER, International Thermonuclear Experimental Reactor. And for them, we will be testing primarily the first wall panels. And our secondary contract is with Eurofusion. And for them, we will be testing diverter mock-ups for the demo fusion reactor. Right now, our priority is the first wall panels. Here are some specifications of the required high heat flux testing we will conduct. 7,500 cycles at 2 megawatts per square meters, where one cycle is 1 minute, composed of 30 seconds of irradiation and 30 seconds of yes. Here are examples of the first wall panels from 3 different manufacturers: Atmostat, Framatome, and a concern of Iberdrola wood lidding. I should mention that these panels the surface of these panels is made from beryllium, which is the reason why Helcha has undergone some expansions in the past year, which I will talk about at the end of the presentation. And I should also mention that we are currently in possession of a panel from Framatome. I apologize, I don't have a picture because we are not allowed to open it yet, so you would just see a closed box anyways. Here is the model of the assembly of the first wall panel as it is connected to Helcha. Here you see 8 copper shielding frames which are used to create a window of predetermined dimensions, so we can so we know what area we are irradiating exactly. I should mention that these shielding frames were created in the workshops in Sidi, for which we are thankful. Yes, so in the past few years, Helcha has undergone a commissioning process. Firstly, for Eurofusion, like I said, Eurofusion, for Eurofusion, we were testing diverter mockups. On the picture on the right, you can see a copper mockup of a diverter. This is not the real diverter that will be made from tungsten or wolfram, which is on the picture on the left here. Here's a small piece of tungsten from which the diverter will be made. And over here is a piece of molybdenum, which was tested in the same way as the tungsten. The tungsten was positioned in this mock-up holder, and it has two copper plates behind it to catch any electrons that miss the target, because it's a very small target and it's hard to exactly hit it. So in order not to make a hole in our vessel, we have to have this kind of beam dump, we call it. All of this is cooled, like I said, with demineralized water. Here you can see the cyclic load that was applied to the tungsten mockup. And here is a slideshow, basically, of the mockup as it was being irradiated. I think, if I'm not mistaken, we reached surface temperatures of 2000 degrees Celsius. Yes, so in this year, we have undergone the commissioning part for the Fusion for Energy contract. One of these, part of the commissioning test was proving the stability of the inlet parameters of the cooling water. We had to prove that we can change all the parameters independent of each other, and they will remain within a defined margin. Here it is 10% for temperature and 5% for flow and pressure from a set value. So here are some graphs of our commissioning test. As you can see, we are mostly within the defined margin. Excuse me. Another part of the commissioning, another requirement, I should say, is uniformity of heat flux. We have to be sure that we are irradiating every part in the same way. As you can see here, this is a copper dummy used for testing, used for commissioning test for the first wall panel. Here are the shielding frames, again, to make a window of predetermined dimensions. And here we used the X-ray Bremsstrahlung that is created by radiation by electron beam. This is a pattern of the electron beam path. It follows this path and creates this X-ray image, which, if we take a profile, you can see it is not very homogeneous. So we have to modify the pattern to allow for a different angle of incidence and different position of the window to achieve a nice homogeneous radiation all around the area. Another part of the commissioning test was a cyclic test. We had to prove that the system can withstand a long-term cycling, as well as the cooling water parameters. Here you can see the absorbed power into the target and into the shielding frames. I should say that this is not exactly the power absorbed by the target or the shielding frames, but it is the power absorbed by the cooling water. So it will be slightly lower than the actual power absorbed by the target because of some heat losses, like from radiation or maybe from conduction to other parts of the assembly. Here is a long-term testing, which took 4 days in total, 1,400 cycles, and the black line here. We were trying to reach the high heat flux of 2 megawatts per square meter, which we calculated by taking the average target absorbed power over one cycle, which is 60 seconds, and this value should be half the power input in the first half of the cycle when the beam is actually radiating the target. So if you multiply this value by 2 and then divide it by the size of the window, we should get 2 megawatts per square meters, which we almost got here. So, like I mentioned, in the past year, there has been some expansions, mainly due to health and safety, because like I said, the first wall panels are, the surface is made from beryllium, and many of you may know that beryllium is very toxic when inhaled in a dust or fume form. So we had to create a series of interconnected boxes that each of them have their own defined under pressure, so that when a door is opened from one box to another, the airflow tends to go towards the most contaminated area, which is right here, immediate to Helcha. Yes, so this is the layout. Here is the 3D model. If I'm not mistaken, then here, where you see the beams, should be the walls separating the 3 buildings. So the middle one is the building number 2, the smallest one. Here's a cross section. And yes, so like I said, the main reason for implementation of this system was health and safety of personnel working in the possibly contaminated area. During the past years, when we were conducting tests with the copper target, we found that it produces a lot of dust, which even the HEPA filters were unable to completely catch. So it was clear that, we had to make some adjustments. And also, maybe more importantly, there was a new European Union directive in the year 2019, which defined how much beryllium can a worker be exposed to in a given time. Lastly, I would like to mention first wall panel manipulator, which was designed by our coworker, Lukáš Kotíšek. This manipulator will allow the moving of the first wall panel into the rooms adjacent to Helcha, and then this top part will disconnect and slide the panel on a ramp, on a manipulating ramp, which is positioned here, connect the panel to the cooling system, and then go out the same way. And lastly, due to the building contamination, we have to implement personal protective equipment for the high contaminated area, which is, if I scroll back, which is the red and the pink one, the closest one to Helcha. The personnel will have to wear more protective equipment, such as this overpressure suit connected to the external air. And in the other rooms, the workers will have to wear these hoods with personal respirators and personal air samplers, which will monitor any potential air contamination that they've come in contact with. So thank you for your attention and for your patience. I'm sorry I was a little long, but if there are any questions.
Okay, thank you very much, Tomáš. Thanks a lot. It was indeed impressive presentation about the new facility related to fusion research. I think it's not only important for us here, I mean, in Czech Republic, but also, as you already mentioned, to European research and worldwide for the fusion. So I will check if there are some questions. Not that I see them. So, okay, then I would like to thank you very much. And we can move to our last presentation. If there is a Professor Mariamma, please, is still there. Thanks for your patience. Sorry for the time difference, but yeah, are you there, Professor? You are muted, but we can see you. Okay, please try again. Can you? Perfect.
Yeah.
Now we can see you and hear you probably as well.
Can I hear me?
Yes.
Hello?
Hello.
Oh, good, good. Yeah, I will try to do this. Okay. Can you see this screen?
Yes, we can see your screen presentation in presentation mode perfectly. So yeah, this is our guest, Professor Mariamma from Nagoya University. Okay, it was scheduled in another part of our conference, but we are happy to welcome you, and it's perfect. It's wonderful that you can still be with us and give the presentation. So I hope that also other audience, other participants will enjoy it. So they are still there. So don't worry. We are all interested in your research, and please, you can start, you can begin. Thank you very much.
Thank you very much, Anna-san. And I would like to express my sincere appreciation for your kind invitation and give me a chance to talk, especially in the consolation presentation. I'm very happy to present on behalf of our Japanese the team about the national Japanese research on concrete degradation and neutron and gamma ray radiation environments. So you know, after the Fukushima Daiichi accident, the situation is very difficult for operation of nuclear power plants. But even such the condition, the government established the 5th strategic energy plan, and in this plan, the government sets the nuclear energy as an important baseload power source. And it is expected that the zero emission ratio, zero emission energy ratio is reached to 44% in fiscal year 2030. For that purpose, we have to operate the some or large number of the nuclear power plants. And for that purpose, long-term operation and the extension of the life of the nuclear power plant is very crucial. And with regard to the regulation in Japan, I would like to explain briefly. In general, we have the regular periodical safety action in the nuclear power plants. And after the 30 years of operation, every 10 years, utilities have to do the technical evaluation of aging reactors. But after the Fukushima Daiichi accident, the life of the nuclear power plant was set to 40 years, but it is possible to extend the lifetime of the nuclear power plant by after getting the permission of through the lifetime extension examination, and the maximum operation period is currently 60 years. And based on this background, the concrete structure is concerned because the concrete is very difficult to replace. So that once the concrete is degraded, it is very difficult to extend life of the nuclear power plant. And so there are several issues are raised to study or to get to do the research with regard to the concrete member. But one of the field about the irradiation environment is the highest concern in Japan. And we have the two kinds of the nuclear reactors. One is a boiling water reactor, and the other is pressurized water reactor. And in these reactors, there's a concrete member which supports the reactor vessel or the shielding the neutron and the gamma ray from the reactors. And this concrete is affected by the neutrons, the gamma ray, for a long period. And the expected the first neutron fluence is more than the 10 to 19 Newton per square centimeters for 40 years. And before doing the research, we use the reference value as a safety evaluation. For neutron fluence, 10 to 20 Newton per square centimeters are used for the reference value, which means that we think that the concrete is safe if the neutron fluence is less than that value. But based on Professor Hilsdorf's the paper, in some countries, regulation says that the 10 to 90 is a critical value, which the concrete degradation start. So based on this background, Japanese Nuclear Regulatory Authority decided to conduct the experimental work. I would like to introduce briefly the result. So we prepare the two different concrete specimens, and we prepare the 6 different kind of aggregates, and cement paste are prepared for the neutron irradiation. And we irradiate these kind of the samples for 4 different neutron fluence. And we, at that time, we used the deep reactor, which has been already shut down. But this reactor is a heavy water reactor, and it means that the gamma ray impact on the concrete is very much reduced, and it is the temperature range during the irradiation is realistic. So for that purpose, we decided to use this one. And then after the irradiation, we found that the surface of the concrete, we see the large amount of cracks on the surface of the concrete. And then we found that after the irradiation, we see the reduction of mass and also increase in the dimension of concrete. So this figure, x-axis is the neutron fluence, and y-axis mass change and the length change. So you see the concrete was expanded at the order of the 1% to 2%. So this is quite huge. So for example, when we do the tensor experiment of concrete, only 200 micron is enough for getting the tensor strength, but the concrete itself was expanded due to some reason. And based on, in addition to that, we do the loading experiment, and we confirm that the reduction of the concrete, and and also the Young modulus reduced dramatically. And we prepared two different concrete, which contain the two different kinds of coarse aggregate. And one is the high amount of quartz, and the other is a general sandstone. And when we use the large amount of quartz in a coarse aggregate, it expanded much, and it showed that's a large reduction of the compressive strength. While the other sandstone aggregate shows a relatively mild reduction, but still we see the reduction of the concrete strength and the Young modulus. So we have to identify the mechanism of this degradation. And we did the irradiation experiment on aggregate samples and do some PIEs. So this is the result. This is the result of XRD, one of the irradiated aggregate. So we show the 4 different levels of neutron flames, and you see that in very small neutron flames, little neutron flames, we see that the peaks, and we clearly see that the peak of the alpha quartz and also albite inside of aggregates. These are the major rock form minerals of the aggregate. But after doing the irradiation, the peaks are reduced some like this. For example, if we look at the peak of the quartz here, we see the reduction of the height like this. And after above the 8/10 to 90s, it has become almost amorphous. We don't see any peaks. And we also found that the albite is a little bit durable to the neutron irradiation, but still we see the reduction of peak like this. So quartz and albite can be affected by the neutron, and it became amorphous. And if we closely look at this peak, we see that some shift towards the smaller angles. It means that the lattice structure is a little bit enlarged due to the neutron irradiation. That is found based on X-ray analysis. And when we measure the dimensional change of the aggregate, and we prepare the five sandstones and 1 limestone. And 5 sandstone has a different amount of alpha quartz. And when we plot the dimensional change of the aggregate after neutron irradiation as a function of quartz amount, we see the roughly linear relationship like this. In case of limestone, there is no expansion, or even we see the little bit the reduction of the dimension. And some of the aggregate doesn't follow the linear relationship. probably this is due to the contribution of other rock-formed minerals such as albite. So therefore, we found that in case of the sedimentary rock, the alpha quartz is very crucial for the expansion of aggregate, which causes expansion of aggregate and the degradation of the concrete. So when we think about the concrete, the binder is the cement paste. So it's a mixture of the cement, or Portland cement, and the water. And when we do the irradiation, and we confirm that the strength change by using the Vickers hardness evaluation. So this is a relationship between the Vickers hardness and the neutron fluence. And as you see, we see the increase in the strength of the hardened cement paste after the irradiation. So it means that the cement paste is very durable, tolerable to the neutron irradiation. This can be explained that probably neutron give some defects of the cement hydrates. But at the same time, due to the high amount of water and the high surface area, we see the water content inside of the specimen. And probably after getting the defects, that hydrates will dissolve and precipitated again, and the defects will be filled through the dissolution of precipitation process. So therefore, the cement paste is quite durable, while the aggregate is very sensitive to the neutron irradiation. Oh, all right. Excuse me. Sorry. Well, so the summary of the Neutron Regulatory Authority project, we found that the concrete is sensitive to the neutron irradiation process, and the compressive strength and the Young modulus are reduced. And linear expansion versus compressive strength ratio showed a good agreement with the previous data, which I didn't show today, but which are corresponding to the degradation of concrete with the free deformation and not the restraint condition. And we found that the aggregate can be expanded, especially the house is very sensitive. And while the hardened cement paste is very durable to against the neutron irradiation. So we found that the source of the concrete degradation is the rock-forming mineral, which affected by the neutron, and which makes the amorphization and show the reduction of the density. So after doing this project, the NRA published the technical report, and which mentioned that the 10 to 90th neutron per square centimeters are threshold to show threshold for showing the reduction of the physical property of the concrete. Therefore, the utility have to defend and have to show that the concrete soundness above the 10 to 90th neutron per square centimeters of neutron fluence. Therefore, the new Japanese project was launched by a Japanese METI. And the new project aimed to, the objective of the new project can be summarized in three terms. One is expansion data of all the aggregates which cover the Japanese nuclear power plant. And the second is the safety evaluation methods and their scientific background for the concrete members affected by the neutrons. And the third is the flux impact. As you know, the acceleration experiment has sometimes wrong data, which we compare to the realistic condition. But unfortunately, we don't have any data about the realistic condition from everywhere. So once the project or the samples harvested from the decommissioning plant, that will be very helpful. But unfortunately, we cannot get any concrete from the decommissioning process. So we have to think about the flux impact theoretically. So we would like to address the thermal healing or say annealing effect of the rock forming minerals and the metamagnetization process. So when think about the evaluation process, expected soundness evaluation procedure, the first, probably, we can use the neutron fluorescence. If we set the certain reference value, and less than that, we can say that this is safe. And once this is violated, and we can evaluate the soundness of concrete by using the concrete strengths of the biological shielding wall or RPV pedestal, the structure. And even if the concrete strength in some part of the concrete member doesn't satisfy the required design strength, in this case, we can evaluate the structural performance. But all of these three, we don't have the enough data. As I mentioned, if we use the limestone is ionic bond, has an ionic bond, and it's very tolerable to the neutron irradiation, and it doesn't show any expansion in the range of the realistic neutron fluorescence for the light water reactor. Therefore, this kind of reference level is a function of the rock forming minerals or rock itself. So we have to do some additional experiment. And when we want to evaluate the concrete strength, we have to evaluate this theoretically. So once we have the relationship between the neutron flux and the reaction ratio of the compressive strength, that is very helpful. And finally, there is no method of the evaluation method of the concrete structure performance, which is partially affected by the neutron fluence. Therefore, we will propose how to evaluate this. And in addition to that, we have to think about the flux impulse, as I mentioned. So we understand the metamagnetization or amorphization process of the rock forming minerals theoretically. So we can explain that how much accelerated experiment is different from the realistic one. And based on that, probably by considering the annealing effect, we can explain that the current situation is quite safe. So we are doing these things. So, and I would like to introduce this one. So we are collecting the rocks from all over Japan. And by considering the previous experiment, we used sedimentary rocks. So in this project, we are doing the experiment on the igneous rocks and try to cover all kinds of rock-forming minerals and try to get the samples. Now we are irradiating these samples. And we are using the LBR-15 nuclear reactor, and as it is recommended to use here, we are put the samples in this hole, and this is the irradiation rig, and we put the 33 samples on each. 33 aggregate samples are encapsulated inside each tube, and we put the 4 tubes in one rig. So this is a very smart way of the irradiation. So after getting the data, we try to analyze which kind of rock formation is very tolerant to the neutron irradiation, and what is which contribute to the expansion of aggregate. We will try to analyze. And for the second, now we are doing the irradiation. Currently, the situation is something like this. So we are still 1 year irradiation period, and then we will do the PIEs. So the results will come after 2 years probably. With regard to the safety evaluation, we are developing the nuclear numerical methods. We call it RBSM, rigid body spring networks, and we model the aggregate and mortar and give the each constitutive load and try to reproduce the mechanical behavior of the concrete, and we can evaluate the concrete property change after the neutron irradiation. And we also try to expand this process for evaluation of biological shielding wall and also the bond behavior between the concrete and the reinforcing burst, and also try to simulate the seismic motion of the cylindrical reinforced concrete member. And based on this background, we will build the constitutive law for the FEM, and we expand this result to the realistic scale analysis. And finally, we are doing the theoretical consideration of the metamorphization of the rock-forming minerals. So one of my colleagues is doing the molecular dynamics and try to evaluate how much of voids are created in rock-forming minerals, and the other colleague is doing the ion irradiation bombardment experiment with a different kind of the ions, and to try to analyze the how much they're analyzing the energy decomposition through the radiosis and the bombardment, and how this kind of energy contributes to the expansion of aggregate. And also he is contributing to the creating the method, developing the method of the PIE by using the TEM. And also we are planning the new irradiation experiment using the same reactor, which we are discussing now. So this is the overall project framework. The highest level is CNW relationship between the United States and Japan. And under the umbrella of this relationship, METI found this research to the Mitsubishi Research Institute. They are managing the research. And Nagaoka University of Technology, Chiba University, Kajima Corporation, and MRA Research Associates contributed to the experimental work and the numerical research works. Shibuya also kindly do the radiation experiment for this project. So all these members are doing the research currently. Now many nuclear power plants waiting for the result of this project. As you see, some of the reactors start to do the extension of lifetime or extension of operation period from 2014. So before that, we have to publish the result of this project. So there is the deadline. So we all elaborate the research to this deadlines. That is the brief explanation of our project. Thank you for your attention.
Okay, thank you very much. We all thank for your presentation. I'll check if there are some questions because there is a delay. Let's wait. And yeah, it's okay. In this moment, it looks like there is no question. It is always nice to see that actually also our institute is in collaboration with such nuclear countries like Japan. So very nice talk and results. Yep. So now there is no question for you, Professor. So thank you once again. Thanks a lot.
Yeah, thank you very much, and thank you for giving me a chance to talk after all the things. I really have to apologize that I misunderstand the time difference between your country and my country. So I totally really sorry that I delayed.
Okay.
Thank you for
thank you. Next time we will meet in person, and then we don't have to solve the time difference. So, okay.
Thank you.
So, thank you very much. And with this, I think we can conclude our conference today. You could hear a lot of things related to nuclear power generation from the materials and issues related to materials, like corrosion, but also you could see the different methods and new methods, advanced methods for actually for studying and investigating the eventual damage caused by radiation, but also by corrosion. So apart from materials, you heard nice talks from area of the fuel cycle and mitigation of radioactive waste. And last not least, it was really pleasure to welcome today, at least via teleconference, our international guests who were summarizing, Lorenzo was summarizing EU nuclear material research, very interesting, and our Japanese guests were showing us their results and work done in their institutes and universities, in also partly collaboration with our institutes. It's really appreciated, pleasure for us. So I would like to thank to all presenters and to our audience, still 65 people watching us. I hope also listening us and bringing back home a lot of knowledge from today. And I definitely have to also thanks to our support team, people who actually made this all happen. So thanks a lot to our support team and technical staff. Thanks. Thank you all.